Welcome to the UGC lecture series. This is the EPG Pathashala lecture series on the subject of computer science, and we are talking about the paper data structures. This module we will be talking about red black trees. We have already spoken about red black trees in the last module. Here where we spoke about the properties of red black trees and how we have to check some conditions for us to do certain rotations and certain modifications. It is not exactly rotation, it is restructuring, because we change the color and so on. We do rotation in some cases. Now, insertion we saw in detail, while deletion we just touched upon. In this module we are going to go more in detail about deletions. So, these are the people responsible for creation of this module. Here we are trying to understand the concept of deletion from red black trees, and we are going to go into detail because deletion is a little more complex than insertion, because we have to keep on doing it till we reach the root node as we did in avial trees, but here a little more color changes and all that. So, to discuss the properties of red black trees that are affected by deletion and to explain deletion in detail from red black trees. So, here we have red black trees, rotation and the red black property. So, as we already know, in binary search tree, deletion itself is a complex operation, because we find the in-order successor or the in-order predecessor. Most cases they talk about in-order successor, and replace the deleted node by the in-order successor. That is what we do in an ordinary binary search delete. So, if a node to be deleted is a leaf, we just delete it. We know this, we are just repeating what is binary search. If a node to be deleted as just one child, replace it with that child, okay, splice it, is a term used here. If a node to be deleted has two children, then what we do? We replace the value in the node by its in-order predecessor or successor's value, and then delete the in-order successor or predecessor, which ensures that by definition that can have only one child. So, this is a recursive step. So, this is how deletion happens in a simple binary search. Okay. Again repeat, leaf, nothing has, you can just delete it. One child, that child has to be moved, has to be attached to the node that is deleted, its parent. If it has two children, then we find, I will keep for here for the simplicity in explanation as successor. We find the in-order successor of the node to be deleted, replace the value of that node in this node, and but before we do that, we have to delete the in-order successor. The in-order successor by definition cannot have a left successor, means it cannot have a left subtree. So, it has only one child. Okay. So, what we do? We delete that using the second condition. So, this is a binary search delete. Now, let us talk about deletion from a red black tree. Now, in insert operation, what did we do? We checked the color of uncle to decide the appropriate case. So, there we had cases. In all the cases, we checked the color of the uncle and certain properties of the Z, the node that where the imbalance occurred. In deletion operation, we check the color of sibling to decide the appropriate case. So, it is slightly different from what is insert. And in delete, the main violated property will be the change in black height in subtrees, as deletion of a black node may cause reduced black height in one route to the leaf path, in one of those paths, because you are doing a what is that, deletion there will be a change in black height. So, that is the basic property that is violated. Remember all the red black tree properties, do you remember? The root node is always black, okay. The leaf nodes are colored black, null nodes, and then the third property is a red node can have only a black parent. The fourth property is the red node can have only two black children, all its children has to be black, only two obviously, if it is maximum of 2 has to have be black. Then the fifth and the main property is the path from the root to the leaf has to be the same for each and every node. So, that is called the black height of the node. That is what I am just repeating what we did in the last module. Now, with that, the main properties that is affected by deletion is the change in black height of the subtrees. So, because especially when we delete a black node, because it may cause a reduced black height. Okay. To understand deletion, let us understand the notation of a double black. So, double black, a concept is used to understand deletion. Okay. So, when a black node is deleted and it is replaced by a black child, the child is marked as double black. So, remember when a black node is deleted, this happens when there are two children, right, and its in-order successor is also black and it is replaced by a black child, then that child is marked as double black. So, we are bringing in a concept of double black. Okay. The main task now is to convert this double black to a single black. Okay. So, that is the main task. So, what all did we say? When we do a deletion, the main property that is affected is the change in the black height, reduced black height or some node, some path from a node, some path that will be happen. Then in order to, that is the property, and in we are using a concept called double black, and the double black is nothing but when a black node is deleted and it is replaced again by a black child, that child is said to have a marked as or is marked as double black, and the main task is to convert double black to a single black, normal black. So, how do we fix the problem? Now, let us assume that we will see the figure, or let us assume that we will see the figure in the next slide. We will think of V as having an extra unit of blackness. This extra blackness must be absorbed into a tree by a red node or propagated up to the root and out of the tree. Very interesting concept. Let us assume you have a node V which has extra blackness, that is the double black. So, what you have to do, either the blackness must be absorbed by a red node, or you have to propagate it up. If that is not possible, you have to propagate it up and push it out of the root. Okay. There are 4 cases. Our examples and rule assume that V is a left child, they are symmetric if V is a right child. So, let us look at this. What color was the node U that was removed? Was it black? Every node is either red or black. Okay. Okay. So, every node is either red or black. Okay. The root is black, it is not okay. If removing, this is what is if the root that is removed is black, every node is either red or black. So, the first property is not a problem. If the root is black, it is not okay, because if you are removing the root, the child that replaces it is red, and so you are violating that property. Every leaf is black, that has no problem even if you delete. If a node is red, then both its children are black. It is not okay, because you are creating 2 red nodes in a row now, because you are deleting a black and replacing it by a red. So, if the node is red, both its children are black, that is violated. And for each node, all parts from the node to the descendant contain the same number of black nodes could change because the black heights of some nodes. So, this is not okay. So, 3 properties are violated, okay, if a black node is removed. What? The root node not being, if it is removed, or the children property, that is both its children are black, that is the 4th property and the 5th property. So, these are the 3 properties that are violated. Now, let V be the node to be deleted, U be the child that replaces V. U is null, then V is a leaf and color of null is considered as black. So, what we are trying to say is V is a node to be deleted, its U is the child of V, either left or right child. Now, if U is null, that means V is a leaf node, and anyway it is considered as black. Case 1, if either U or V is red, okay, that is the first case. Remember, V is a node to be deleted, U is a child that replaces V. If either U or V is red, that is considered as the first case. If both U and V are black, that is considered as the second case. So, we will see each of these cases. If either U or V is red, we mark the replaced child as black, there will be no change in black height. Okay. So, if U or V is red, now suppose you delete 20, if you delete 20, what will you do? You will put 10 as the child of 30. So, that is U, this is V. So, either U or V is red, in our case U is red. So, we mark the replace child as black. Okay. So, use I am sorry, V is the child being deleted and U is the child that replaces it. This replacing here is not only the binary search tree is both child that online successor replacement, it also means that one child. If it is leaf, it is no consideration. If it is one child, also this deletion. So, this is an example of that. It has only one child, that is we are deleting 20. So, V is the node to be deleted and it is replaced by u, okay, with one child only. Now, what we do here, if you delete 20, we mark the replaced child which is u as black, and there is no change in the black height, because one of it was red. U and V cannot be read as V is a parent of U, okay, and two consecutive reds are not allowed in a red black tree. So, in this case U and V cannot, both cannot be read. If both are read, it is violated. So, both cannot be read because of the fact that two consecutive original tree, two consecutive reds cannot be. So, that is if either U or V is read. Okay. Now, let us consider the case both U and V are black. So, that color U as double black. Now, our task reduces to converting this double black into a single black. Okay. So, if V is a leaf, okay, remember what is V? V is the node to be deleted, then U is null and color of null is considered as black. So, the deletion of a black leaf causes a double black. So, let us take this case. Now, what we are doing is we want to delete V, which is 10. Now, V is a leaf, U is null and the color of null is black. So, the deletion of the black leaf V causes a double black. So, you delete 10. So, this null gets a double black. You would have thought null does not come into the picture, but null gets a double black. So, this is a first case. Okay. So, this is what is called as a double black. Now, let us look at bottom up. Now, there are two types of deletion. We are looking at bottom up deletion. We will not look at top down, that also is another method of deletion. So, do ordinary BST deletion, eventually a case 1 or a case 2 deletion will be done, that is either it will be a leaf or just one child. If deleted node U is a leaf node, think of deletion as replacing U with the null node pointer V. If U has one child, we think of children replacing U with and V. What can go wrong? Now, when this happens, that is case 1 and case 2, leaf and one child deletion, node having being a leaf or node having one child, then what happens in that case? What can go wrong? Which RB property may be violated after deletion? That is the problem. That is, if U is red, remember U is the child that replaces, it is not a problem because no RB properties are violated. But if U is black and U is not the root, deleting it, okay, U is black, deleting it will change the black height along the sum path. So, that is our problem. So, now let us look at if U is red, not a problem, no RB violated. If U is black, U is not the root, deleting it, because if it is the root, no problem. If it is not the root, deleting it will change the black height. Root, it will not be counted anyway, so it does not change. That is why we are looking at taking it out. So, think of V having an extra bit, extra unit of blackness, which we discussed before. This extra valence must be absorbed into the tree. Again, we are repeating that by a red node or propagated up the root and out of the tree. There are 5 cases. Our examples and rule assume that V is a left child, symmetric for this. So, let us now talk about the node just deleted was U, the node that replaces it with V, which has an extra unit of blackness. The parent of V is P. Okay. The sibling of V is S, okay, and this is a black node, this is a net node, and this is red or black and do not care. Let us take first step is examine the root. If both the root children are black, make the root red, move V to the appropriate child of the root, proceed to step 2. Otherwise, if it is not true, otherwise designate the root as V and proceed to step 3. So, let us look at the cases in step 2, that is the recursion. As I will just repeat again, what we are doing here is the first step is both the root children are black. Okay. Make the root red, move V to the appropriate child of the root and proceed to step 2. Otherwise, designate the root as V and proceed to step 3. So, we are looking at the different steps of step 2. As we traverse down the tree, we continually encounter the situation until we reach the node to be deleted. So, V is black, parent P is red, sibling S is black. We are going to color V red, then recolor other nodes and possibly do rotation based on the color of V's and S's children. Okay. So, 1 to 4 V has 2 black children. Okay. Case 1, sibling S of V is red. Case 2 to 4, sibling S of V is black. S is black and S has 2 black children. S is black and S right child is red and left child is black, either we are not bothered. Case 4 is S is black and S right child is black and left child is red. So, these are the 4 cases we will be looking at. Case 5 is V has at least one right child. Now, let us look at an example. This is an example. V has 2 black children. So, sibling S of V is red. Okay. So, V sibling S is red. Now, what you do is rotate S around P. P is the parent of V as we saw, and recolor S and P. So, it is not a terminal case, one of the other cases will now apply. All other cases are when S is black. So, this is the only case when S is red. So, when V has 2 black children and the sibling is red, this is the case. So, what do? It's we rotate S about P, that means it is a left rotation, rotate S about P, and that is the parent of V, and recolor S and P. So, we rotate it, left rotate is S about P, and we get this. And what did we do? We recolor this. So, this is S and P, then recolor S and P, and so this is the final tree. So, this is the case where V sibling is red. So, what did we do? We replaced, we left rotated S about P and recolored S and P, interchange the colors of S and P. So, this is when the V sibling is S is red. Now, we will so that is what we did. Now, case 2 to 4, this is bottom up deletion. So, now S the sibling is black, that is where V has 2 black children, there also we had 2 black children, but S sibling of V is black. In this case, what do we do? So, that is the first condition, this is the second condition, S is black. Now, okay. Now, S's left child is red. If both of the children are red, we can do either 3 or 4. So, that we S left child is red and S right child is red, those are the 2 cases. S's. So, V's sibling S is black and has 2 black children. Then recolor S to be red, P absorbs V's extra blackness. If P is red, we are done, it absorbs the blackness. P is black, it has extra blackness, and the blackness is propagate up the tree. Okay. So, V sibling S is black and has 2 black children, the previous case we saw. So, what do we do here? It has 2 black children. So, just recolor V, P and S and move down the tree. So, what did we do? We colored S is red, P as black and V as red, and we just do this. So, the other cases, so sibling S is black and has 2 black children, recolor S, P absorbs the, so you have recolored S. Okay. Then if P is red, done. If P is black, propagate black up the tree. Either extra black absorbed by P, or now P has extra blackness. So, that if it is red, it would have absorbed, if it is not, it would have double blackness. So, this is what we mean by replacing node having being a black and getting an extra black. Now, sibling is black and both, this is an example of that. So, let P be the subtree of a complete tree, it is not a complete tree. Now, here you have S sibling is black and both his children are black. So, perform recoloring and recur for the parent if parent is black. So, now you have a double for the parent. So, that becomes we have done everything, and what we did is we colored S as black, S as red, and what did we do? We colored P as whatever P was, we wanted black. So, now it becomes double black. So, recur for 20 to remove double black from it. So, again you have to consider that and do some operation for us to remove the double black from it. So, the case 3, yes, right child of parent P of V is black, that is the previous case. S's right child is red, left child we are not bothered about. So, one extra red is there. Rotate S about P and swap the colors of S and P and color S's right child as black. It was red, now colored it as black. This is the terminal case and we are done. So, this is the final case. When this happens, you do not absorption has happened. So, that case S is black, S's right child is red as you can see. Now, rotate S about P. So, S is rotated about P. So, you know how it is a left rotate. So, it is rotated about P and you recolor V, P, S and R. So, R which was red is replaced becomes black, S which was black is red, P which was red is black and V which is black is red. So, you are recoloring everything. Recoloring means it changes from one color to the other. So, this is the terminal case of what will happen. So, again we are considering the same case. So, sibling S is black and has right child as red and the left child is any color. So, left rotate S about P. Okay. So, rotate S about P. So, you can see the child there. So, rotate about P. So, swap colors of S and P. So, that happens and color S's right child as black. So, that is what we did, swap the colors and color. So, terminal case and we are done. So, as you can see the absorption has happened. Now, let us take a case and see what happens. S is a right child. So, this is here S is a right child of its parent and R is the right child of S or both its children are red. So, one of the children has to be red, that is all the condition here. So, now what happens, LR plus swap colors, left rotation plus swap colors and color R black. So, that is what we are going to do. Here left child S is red. So, delete 20. So, we want to delete 20. So, there you have a double black and that is a parent. This is S, the sibling and this is the child R which is red. Okay. Left child is also red, that is okay. Now, what you have to do is you have to that is you. Now, what you have to do is you have to do that left rotate. So, left rotate means S becomes a parent. So, 40 becomes a parent and swap the colors of S and P. So, S is 40 and you are swapping 40 and 30 and here there is no effect because both are black and color R as black. So, that is what you have done. So, the next case is S right sibling of V is black, S's right child is black and S's left child is red. So, rotate S left child around S. So, one more extra rotation, swap the color of S's and S's left child. Now, we go back to case 3. So, the problem with deletion is you will always finally have to come up with one case where you terminate. Okay. So, here we have S is black, S's left child L is red, rotate that left child around S and then rotate LC around P, recolor V and P and then continue down the 3. So, let us take this case. You have S is black, S's left child is red, that is what we have written here, right side is red. Now, the first step is rotate LC around S. So, that is a right rotation, LC around S. So, if you do LC around LC around S. Okay. So, if you do LC around S, S will go there and you have LC and then rotate LC around P. So, you will first rotate LC around S. So, S comes down and that LC is rotated about P. So, LC goes up and P comes down and recolor V and P. So, that is what is done. So, sibling S is black and has right child black and left child red, that is the previous case we saw. Right rotate S's left child LC around S. So, right rotate that. So, you will get this, you have done that and so LC is rotated and S comes down, P is still there. So, that is what you did and swap the colors of S and S's child. So, you swap this colors. So, that is swapped S and S's left child, that is LC. So, that is swapping has happened and then what you have to do is you have to rotate. So, after this you have to do a so first you have done a right rotate, then you have to do a left rotate and finish it. Okay. Now, you see the example 4, S is a right child of its parent and R is a left child of S, right child of its parent. Okay. And U is here, this is the deletion of 20. So, you have a double black and that is V plus, and that is a parent, and that is S, and this is R, it is a left child. So, the first rotation what happens, this is what will happen, you are rotating the left child R about 40, okay, right rotate, and then you do the second rotation. So, you rotate 35 about 30. So, that is what is happening, and so you have two rotations here. Now, suppose V has at least one red child, continue down the 3 to the next level. If new V is red, continue down again. If new V is black, S is red and P is black, rotate S around P, recolor P and S. Back to the main case, that is case 2, cases 1 to 5. All this was within the step 2 where we did all the cases. So, everything is to do with sibling. So, you have V, you have S, S is V's sibling, sibling has one left child which is red, both are black, one is red, other is red, both are red, and then its parent and so on. So, that those were the 5 cases we saw. Next is eventually find the node to be deleted, a leaf or a node with one non-null child, that is a leaf. Delete the appropriate node as a red leaf. So, color the root black. So, that is the steps that we have. The top down is a alternative to this, to the recursive bottom up, it is a top down deletion. So, this method is iterative, it moves down the tree only, fixing things as it goes. We are not looking at top down, we have looked only at bottom up, because we started from the node, and as we go along we keep on seeing whether a double black occurred and try to change it. So, the summary of this is we explain the concept of deletion from red black trees, we accept the concept. Now, the concept was that we introduced something called double black. What was double black? If a black node was deleted and that had to be replaced by a black node, then that replaced node gets a double black. So, that was what was called a double black, and our deletion principle was to remove this double black. Now, the problem is how do you delete how do you remove this double black? Either it has to be absorbed by a red node or it has to go out from the root. So, that is what we were trying to say, you are just from the bottom you are taking it up to the root and removing it. Okay. So, that is what we were trying to say. So, there were many cases, but the important concept was the node and its sibling. While previously we had a wherever that double blackness is coming, we had a, that is the node we call V, that node had a sibling. Now, the sibling could be red or black. Okay. Of course, this node has 2 black children, that is what we are assuming. Here we have the sibling node could be red or black. If it is black, fine. If it is if it is red, fine, easy case. If it is black, then we are looking at the children of that sibling, and depending upon the color of the sibling we have different cases. But remember, when we do each of these cases, we still have propagate the blackness up the tree, and if it is what we encounter is a black node, whatever we want to replace. If it is not, if it is a red node, we can replace it. If it is we can absorb the blackness. If it is a black node, then there is a double black again, and it has to be propagated up until either we reach a red node that can absorb the blackness, or we reach the root node such that it goes out of the tree. So, we discussed the properties and which are affected by deletion. Remember, the basic property that was affected by deletion was the change in the black height. That is why we have this double black. We wanted to know that what is this double black exactly? Double black tells us that please note that the black there is needed. So, do not remove it. So, that is what we were trying to do by recoloring and things like that. So, we explain the deletion operation with some case examples. So, with this we finish 2 main balanced binary search trees. One was AVL trees and one was red black trees. We have another one which we called splay trees, that was again balanced binary search trees, which we will cover in the next module. So, with that we finish red black trees. Both in the previous module we discussed the properties and the insertion, and now we discuss deletion. Thank you.